I work with a lot of enterprise customers, and the biggest question I get from them is, how does Google do it? How does Google build globally scalable services that, for the most part, stay up? Things like search, YouTube, Maps, Gmail. So today I thought what I would do is I would actually take you behind the curtain and let's take a peek at what that platform looks like from the eyes of a service mesh. We've all heard things like Istio and Anthos service mesh, but what do they mean and how do I build globally scalable services with that? My name is Amir Abbas. I'm a solutions architect out of San Francisco, and I focus on distributed platforms, specifically with service mesh in mind. So this is kind of what we're going to talk about. We're going to really talk about what does your application actually need and what kind of choices they have when it comes to putting your application on a platform. We're going to talk about multiple Kubernetes clusters and what does that mean for distributed services. So most of us are kind of getting into the world of containerization, and containerization and Kubernetes are kind of synonymous. So I'm going to take that one step further and talk about multiple Kubernetes clusters. Then we're going to take a step back and really look at why service meshes exist. Then we're going to look at the actual service mesh implementation with Istio and Anthos service mesh and how they actually perform and what they actually do. And then we'll bring all of these concepts together and build a platform that can run globally scalable, resilient services. So let's get started. Let's start with an application. Typically, we think of from a very infrastructure platformy point of view, right? We think of what does the platform need? I want to kind of flip that model and let's talk about what do applications need. And applications have a lot of choices. Just in GCP, we have these kind of three main compute choices. On the far left-hand side, you've got platform as a service with App Engine. This is a very opinionated system that you use. On the other hand of the spectrum, you've got compute engine. This is infrastructure as a service. Doesn't give you anything, but it gives you a lot of flexibility. You have to build the entire platform yourselves. Now, both of these are very extreme. On one side, you're very opinionated, can't bring in any of the opinions that you'd like. On the other side, you're maybe too unopinionated, and you have to do all of the work and all of the operations and management yourself. But then along comes Kubernetes, and it gives us a really nice kind of a middle point. It gives us that automation and abstraction away from infrastructure, and it gives us that declarative way of deploying applications. So great, let's deploy our applications on Kubernetes. But what we've learned is that you typically don't deploy the applications right on Kubernetes. Kubernetes is a great scheduler. It's a great container orchestration solution, but it doesn't give you everything, right? You need to still build a platform on top of Kubernetes, things like observability and security and software delivery. That all needs to happen up top of Kubernetes. So all of those opinions that you bring in kind of puts you in the middle of this very opinionated paths and somewhere in this Kubernetes. And this is the arrow where that arrow sits is kind of what we're going to talk about today is where that is. Let's talk about Kubernetes. So most of us have at least started to take the journey into Kubernetes with container orchestration and stuff. So why do we need multiple clusters? Well, since we're talking about building globally scalable services, by definition, we're talking about multiple locations or multiple regions. A Kubernetes cluster can only reside in a single region. So if you're in 2 or more regions, you're already in multiple cluster land. Now, within a region, when I talk to customers, they talk about, well, how do I make my services resilient within a region? One way to do that is to have multiple clusters within a region. 2 is better than 1. If 1 goes down, you have something else. So we want to just kind of focus on those 2 aspects: multi-regionality, clusters in different regions, and regional resiliency, multiple clusters in a single region that gives you that. And this kind of spawns this idea of something called a distributed service. The challenge with the Kubernetes service is that Kubernetes service's fate is tethered to the fate of the cluster that it runs on. Now, a service is a very important thing. That's your revenue generator. That's what makes you money. A cluster is just a piece of infrastructure that just runs your platform. It actually costs you money. So tying those 2 or tethering those 2 together kind of doesn't make sense. Distributed service, at a very simplistic definition, is how can I put the same service on multiple Kubernetes clusters? That's what a distributed service is. It's a very, very simple concept. What it does is it abstracts your services lifecycle from your cluster lifecycle. If I'm running on multiple clusters, I can have clusters going up and down, and my services can remain up. Visually, it would look something like this. So here, I am representing 2 regions. On the left-hand side, I have region 1. On the right-hand side, I have region 2. And then we have multiple clusters in each region. So on the left-hand side, we have 2 zonal clusters, 1 in each zone A and zone B. And on the right-hand side, I have 2 zonal clusters. And I have a single distributed service running on all these 4 clusters. So not only do I have this service that spans multiple regions, but it also spans multiple clusters within a region. So I'm getting scalability and I'm getting resiliency, right? I want to plant that idea because it opens up a lot of extra knobs when you think in terms of distributed services, right? Things like I have to look at service level objectives at a service layer, not at individual workload running on each of these clusters. If I can provide my users with the SLO that I've promised them, it doesn't matter whether it's running on 4 clusters or a single cluster. Capacity planning becomes easier. We've heard terms like N+1 and N+2. If N is the number of clusters that I need to run and satisfy the requirements for capacity for a particular service, then N+1 and N+2 is, can I withstand a single failure or a double failure? So we typically think of in terms of N+1 and N+2. Can't do that with a single cluster. Rollouts and rollbacks can be done at a very granular level, right? So instead of pushing out a new version of your service to a single cluster or to every single cluster, I may want to just push out that new version to a single cluster in one zone and just have a subset of my users use it, test it out, and then kind of roll it out to every single other cluster. Internally at Google, we use terms like draining and spilling, and it sounds exactly like what it means. If a cluster is having an issue, or if I want to upgrade a cluster, I can drain traffic away from that workload running on that particular cluster and spill it to other clusters. So I still haven't taken my service down, but I've now freed up that cluster, and I can do whatever maintenance or operations or upgrades that I want on that cluster. So you can kind of see that when you think in terms of distributed services, a lot of these kind of resiliency and scalability knobs just kind of open up to you. So I want to park that idea, and let's switch to why service meshes exist, and then we'll bring these two ideas together. So for this, I'm going to kind of go back in time and look at this monolithic application that we've heard so much about. And what is a monolithic application? It's just a collection of functions. But the first thing is a monolithic application is not a bad thing. It's actually a very deterministic, it's a very good thing. When function A calls function B, it always works. And it always works in a very deterministic way. It's a function call. I don't have to worry about, is the function B going to respond or not? It is going to respond. If it doesn't, I can just look at the logs, and it's usually the problem is in the code, and I can just go ahead and fix that. Then someone smart comes along and says, we're going to containerize everything. And all that means is I'm going to take those individual functions and I'm going to run them as individual quantums of compute. And that's what a container is, just functions running in containers. So the first thing we've done is introduce this concept of a network. Now, this is the crux of why service meshes exist. This is kind of the bane of the problem, is that we've taken a function call and we've converted that into a network call. So the first thing we need is we need a different way to connect these two things together. We need an interface or an API, for example. Most languages come with their own APIs, or you can use an open source API library like gRPC and stick that on, and now you're good. You've got your client stubs, you've got your server stubs. These things can talk to each other. Well, that's great. We've kind of solved just the connectivity problem. What about security? We've heard these terms, zero trust network. At a very simplistic term, all that means is I'm not going to trust any form of a network, whether it's an external internet or whether it's an internal intranet, right? So in traditional terms, what we typically do is we really fortify the periphery of our networks with very solid big iron firewalls, and we make them very, 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 very strong. So it's very hard to penetrate those walls. But as soon as you're in, we just implicitly trust everything on our intranet. As you get into the world of containers and distributed systems, we've realized that even within the network, we need an extra layer of security. And this is the concept of zero trust network, whereas we're not going to trust any network. Each container and each service must be able to identify itself. And this ID becomes a very important concept. So that's the first thing we need, is now every service must have an identification, must have somewhere to identify itself to other services. Now, if I'm a developer, and let's say I'm just starting into the world of containers, I would go and Google, Python or Go security libraries, and I would get these libraries that kind of do this for me. And I would just implement those libraries as part of my code. And now what I've gotten is I've gotten things like authentication. I can authenticate myself to other services, maybe even authorization. Am I allowed to do certain actions to other services? And I can get things like encryption. Because we don't trust the network, we don't want to have open communication between these two things. Now everything is encrypted. It doesn't have to happen over a VPN or over the same network. The next thing we need is this idea that networks are not resilient, right? Networks are very unreliable. When networks go down, what happens? When container A calls container B and container B doesn't respond back immediately, what do? Do you retry? How often do you retry? When do you stop? You can build that logic inside of your code, or you can get a network resilience library. Again, as a developer, I would go on Google, I would Google something, I would get a library, I would slap that onto my container, and great, now I've taken care of these kind of network idiosyncrasies, latency, fault tolerance, things going down. We'll talk about circuit breakers shortly. Since everything is now on a network, and networks are not infinite resources, We need to figure out how to put network policies on things. How often can container A call container B? We don't want to bog down container B if container A is just hammering this. So we need to be able to put some sort of rate limits and quotas on a per service level, and maybe even granularly on individual services. So now I need some sort of a network policy. And then last but not least is observability, which is probably the biggest and the most important thing when it comes to distributed systems, is what is happening in my environment. Previously, everything was kind of hidden in the logs. I could just look at the logs in a monolith and I could see, oh, this function has this error and this function is not working. But now I have, is the problem in the network? Is the problem in a request? Is the problem in the API? Is the problem with security? So I need to measure a lot of things. Things like metrics, network metrics, things like distributed tracing. Most of the time, you're not just talking about 2 containers. You may be talking about hundreds or thousands of containers, and a single request can traverse a lot of different services and a lot of different containers. And things like topology. I just want to see what my topology looks like, which services are actually talking to other services. Now, if we put a box around all of these features that we need in the middle, they all exist because you have decided to take a monolith and put those things on a network. These are not your business logic. These are not the things that make you money. And these are very network functions oriented thing, right? This is something you absolutely need. You cannot live without these things. You have to have them somewhere. What a service mesh proposes is, why don't, instead of putting all of this logic into every single container and as part of libraries, is there a way to separate your business logic away from those network functions? And what that visually would look like is, I want to take this picture and I want to convert that into this. I have my business logic now abstracted away from all of my network functions, my identity, my observability, my policies, my authentication and authorization. Since we live in a world of containers, we can toss both of those things in the container. And in Kubernetes, we can put multiple containers inside of a pod. Now, this is called a sidecar pattern, where you have kind of your primary container, that's your application container that's running up, and then you have kind of a sidecar container that's providing additional functionality to that primary container. And that sidecar container suspiciously looks like a network proxy because it's providing a lot of network functions. Envoy is a very popular proxy that's used in distributed system, that's used for client-side load balancing, because now I'm going to slap this Envoy proxy to every single container. There are a lot of operational benefits to this too. I have a very clear kind of lines of delineation between roles and responsibility on who's doing what. Above this blue line is my business logic, are my application developers. They can just now focus on developing the application. Below this line are my operators. They can focus on building the platform, putting policies on the platform, enforcing those policies. This is, to me, the kind of the true definition of portability. This container now can run anywhere as long as those functions is provided by the platform. And now I've relegated these additional network functions onto the platform layer that are managed by experts that know how to manage networks, how to manage security, how to manage observability. So let's look at an implementation of this. How do we implement this thing? Istio and Anthos Service Mesh are just 2 of the implementation. Istio is an open source implementation of a service mesh. Anthos is a Google managed service mesh that uses the same APIs, uses the Istio APIs. And I'm going to build the control plane and the data plane at the same time. And I'm really just going to focus on the functionality because I think that's the important bits, and the implementation is not as exciting. So on the data plane, we have a bunch of pods with the Envoy proxies running on each pod. And then we have this control plane. And the first thing we need to know is that Istio and ASM needs their own service registry, which is nothing more than just a list of all the services that are running in the service mesh and all of the endpoints on how I can get to it. So these are the IP addresses of each of the pods. These could also be the IP addresses of each of the VMs. Right? So, and it doesn't matter where these pods are running. They could be running on a single cluster or multiple clusters. With this, I get additional kind of benefits of traffic management. I can do very granular things. For example, if I'm deploying a new version of service B or pod B, which is pod B prime, and I only want to send a subset of the traffic there, now I can do things like, hey, I just want to send 10% of the traffic to the new version, and 90% of the traffic remains of my old version. I can test out the new version, everything looks good, and then I can slowly ramp that new version up. Observability, where previously we talked about logging was the only thing in Monolith that was important, but now we need network observability, network metrics, distributed tracing. Because these envoys are placed in a very kind of a fortunate position, they wrap up all of these metrics and they emit those in Prometheus specs, and then you can send them to any collector you'd like. So with Istio and Anthos Service Mesh and GCP, automatically we ingest them into cloud monitoring, which is previously known as Stackdriver, but you can use any collector you'd like. Security was another thing that we wanted to talk about, right? It's a zero trust network. We don't trust the intranet. We want everything to be encrypted. These envoys now are kind of the holders of your identity, and they hold a strong identity. They hold certificates. A certificate authority with the shared common root, can now furnish the certificates to each of these envoys. And on the basis of that, they can now authenticate to each other, and they can also do TLS and encryption between each other. Policy, not only just network policy. We talked about network policy, right? As, for example, pod A wants to talk to pod C, and maybe we've limited that to only do 100 requests per second. But authorization, role-based authorization too, which is what can actually pod A do to pod C, right? So it can do a get and a post on these particular API endpoints. That can also be done through Istio and through the Envoy proxies. And last but not least is the platform and the service resiliency. A circuit breaker is a common pattern that's used in production per service, right? So this is this idea that if a service is having an issue, we want to be able to fail that service as quickly as possible and take countermeasures against it. So let's say we have a flow that goes from pod A to B to C to D, and D is having problems. Instead of that flow just continuing to run and eventually just kind of cause backwards cascading failures, we want D to quickly identify that I'm having some issues, and the other services can then just take countermeasures and precautions on top of that, right? So in this case, let's say we put a rule that says, if I see 5 consecutive HTTP errors, just consider me down, go around me, do something else, notify the user, tell them to wait or back off, or any of these logics that you can put in. And fault injection is something you can do to test the resiliency of your application. So how would my application work if I injected a 10% error rate, or if I injected a 10 millisecond delay? This is also something one of my customers used to actually test something where they wanted to deploy it into a different region that was about 50 millisecond away. And instead of spinning up an entire infrastructure in that region, they just simply injected a 50 millisecond delay and just tested and observed what their services are going to do. So these are kind of the 6 features and functionality of the control plane that are above and beyond what Kubernetes gives you. The service registry works across multiple clusters. Traffic management can happen at a very granular service per service level. Observability gives you extra things without having to instrument your thing. You get security and policy above and beyond what Kubernetes gives you. And then you get resiliency on when Kubernetes is having problems and services are having problems. How can I automatically recover from those particular services? So that's great. So we have this distributed services concept. We have this concept of a service mesh. Let's build a platform together, and let's build that on GCP. So the first thing I'm going to say is that a lot of these concepts can apply on non-GCP environments too. And we're only going to build one environment. So think of this as this is my production environment, and I'm about to onboard a service or a product in multiple regions. And we're going to just pick 2 regions, because if you can do this in 2 regions, you can do this in 20 plus regions. So everything starts with a network. And what we want to do is we want to have a nice flat network. It makes communication between pods and other services much, much easier. And we want to kind of wrap that around into a single network. In Google, we have a concept of a shared VPC that can be shared to other projects. So we have this one project, Project 0, that's owned by your networking team. And it gives them a centralized control. So instead of giving every single team their own network, you have this one centralized network. They control the ingress and egress out of that particular network, and it makes it much easier for services to communicate with one another. Inside of that, we have projects. Now, project in Google is just a collection of resources owned by a certain team or by a certain function. So in this case, we're just representing 2 projects. We have a platform admins project that's owned by the platform admins team. That's your operator team. And then we have this product 1 project, right? That's owned by a single product team. And imagine if you had multiple products, then you would have project 3, project 4, and so on. When I think of projects, I think of 3 kind of levels of controls. Billing is done at a project level. So anytime I want separation of billing, so by environment, by team, by function, it's a good way to put a project boundary around it. Access management is done at a project level. So things that are owned by, let's say, the platform admins team should belong into the platform admins project, and things that are owned by the product team should belong to the product. And last but not least, quota is done at a project level. So where you don't want to share quotas between different teams, it's much easier to just put a project boundary around it. We also put environments in separate projects. So here I'm showing a 3-project setup for, let's say, the prod environment. You would have a very similar setup for dev and stage as well. Then inside of these projects, we put subnets. Subnets in GCP and Google are regional, and we recommend you use as lowest number of subnets as possible. So here I'm representing 2 regions. On the left-hand side, we have region 1. On the right-hand side, we have region 2, and we have 2 subnets, subnet 1 and subnet 2. You can have more subnets, but it's much easier to expand a single subnet than to have smaller subnets where you didn't maybe size them right the first way. IPAM, IP address management, becomes much easier. You have to start thinking about how many IPs do I need for nodes, how many IPs do I need for pods, which are the biggest kind of resource hogs for IPs and for service IPs. We always recommend using custom subnets, so not having IP wastage. by having these automated subnets. Inside of those subnets, you have your Kubernetes clusters. Now, these are your Kubernetes clusters that are there for applications as well as for operations. So in this case, we're showing 6 clusters set up, and they're both identical. There's 3 clusters in region 1, 3 clusters in region 2. If you want other regions, you can think about horizontally scaling this out and basically stamping this exact environment in other regions as well. We have kind of these colorful clusters, the orange, red, blue, and green. Think of them as your application clusters. This is where your actual services that are used by other services or used by your customers are actually going to sit. We'll call them apps clusters or application clusters. Then you have these 2 clusters at the bottom, the gray clusters. Think of them as your operations clusters. This is where your shared services are going to sit. This is things like CI/CD, tooling, observability, or in this case, the ASM or the Istio control plane. By separating out your applications cluster and your operations cluster, we've kind of separated out the life cycle of the 2. We want to manage those independently of one another. Your applications probably will have a much higher scrutiny for SLOs and stuff, and maybe they're not being upgraded as often, and we want to maybe really kind of take care of those, as opposed to your operations clusters, which can go down for extended periods of time, and it may or should not affect too many things. So by separating those 2 clusters out, I have kind of granular control over how I upgrade and how I maintain and operate on these clusters. We start with a single ASM control plane per region. We can put a control plane in every single cluster. That's a perfectly viable design. And if you have a small number of clusters, as a matter of fact, that is what's recommended. But then we've realized that as you grow, as you go beyond, let's say 20, 30, 40, or 100 clusters, then you would have 100 control planes, and it becomes kind of an operational challenge and a nightmare to kind of manage those. We also do a single control plane per region. This way, you're not dependent upon other regions or regional connectivity or even latency. Within a region, your latency is very, very small. We put the control plane in the ops cluster at the bottom, and now you can just continue to add application clusters, and they all connect back to that single control plane. And we've already talked about the separation of lifecycle management as well as ownership, where your application clusters and your operation clusters could be owned by different teams. So now you have, even though it's logically a global mesh, but you have these kind of regional meshes that are kind of in a shared control plane model. So you have a single control plane sharing all of the clusters within that region, but both of these control planes have the full picture of the entire infrastructure, right, of every single cluster. Then comes in namespaces. Namespaces is a very important concept when it comes to service meshes. In a globally scalable service mesh, in a single logical global service mesh, a namespace across multiple clusters is assumed to be the same thing. So in this particular case, if I create a namespace called product1 namespace on 4 different clusters, and I have workloads running in these namespaces, from the Istio service registry or the Anthos service mesh service registry perspective, it's considered a single distributed service. Aha, got that word back, distributed service. So we're starting to talk about that. I'm getting regional redundancy because I have multiple clusters within that region. I'm getting global redundancy because I'm running the same service now across multiple clusters. I'm also utilizing my clusters better because now I can create namespaces as these landing zones for my services. I don't have to create separate clusters for individual services. Namespaces are the landing zones for, in this case, product 1. And that's what I'm renting out or I'm giving out to that particular service. If I have product 2, product 3, product N, those will all be namespaces that are placed on these clusters, all part of the single global service mesh. And service meshes can talk to each other, whether it's running in one cluster or multiple clusters. And since all of these clusters are on a flat network, I never leave my VPC. Everything is done on the same virtual private cloud. So think of namespaces and landing zones, and think of multi-tenant clusters always. Multi-tenant clusters give you the best resiliency. So even in this example, I've got a product 1 service running on 4 clusters. Technically, again, I can lose 3 of these 4 clusters, and I've never lost my service, right? So I can lose an entire region and part of my other region, and I have not lost it. Versus if I had individual clusters that I'm not kind of amortizing between different services. Right. Now these product 1 services can talk to other GCP resources that are running in project 2 in that particular product's team. So this is kind of a good way to kind of think about how to manage multiple clusters in multiple regions, how to overlay a service mesh on top, how to think about project hierarchy as well as networking, how to think about IAM and controls. What we see is a good way to kind of think about globally scalable services. And by the way, this is how Google builds services internally. If you want to learn more, and if you want to build exactly what I showed you, you can go to the first link, bit.ly/ASM-workshop. That will give you actual Terraform scripts to build exactly what we showed. as well as you can learn about how to deploy applications, how to secure applications, how to observe them, and so on. And if you want to learn more about multi-cluster lifecycle management, well, now I'm going into 6 or 7 or 8 clusters. How do I upgrade those clusters, and how do I manage and operate multiple clusters? You can learn more on the blog series I wrote. It's a 5-part blog series on the second link, which is bit.ly/GKE multi-cluster lifecycle, that shows you how to upgrade one cluster at a time and different strategies of managing, monitoring, and maintaining your multiple cluster environment. Thank you very much.